is from our school here at the University of Queensland School of Mathematics and Physics, and he runs very substantial activity in quantum information and quantum computation, and his claim to fame, or his beautiful experiments, are, or have been and continue to be, on all linear quantum computing, cryptography and quantum computation. You will have a chance to see the labs. That will be on Friday afternoon as the last activity of the school. We'll take you through the labs at our school. So one of the labs will be visiting all the areas. So Andrew is Federation Fellow, which is a position proudly held by a very small number of Australian and foreign scientists in Australia, and the fellowship rewards outstanding achievements in science and in this case, it's quantum information and computing. So, Andrew.
Thank you, Helena. So just before I get started, two comments, I guess. The first comment is, of course, feel free to interrupt and ask questions at any time. Otherwise, I'll just move far too quickly through material. The second comment is, Richard Feynman said, never underestimate the audience, the pleasure an audience gets from hearing something it already knows. So given that that's true, the first little bit of this talk I think you'll find deeply pleasurable. But don't worry, we'll get to the hard stuff soon enough. In case you're wondering, that photo is from Australia Day in Western Australia in 2007. And I like this photo because on the left you've got fireworks, on the right you've got lightning, and right in the middle, you probably can't see it, there was the comet that was visible that year. It's just a very nice spot to be. Okay, so photonic quantum computing. We're going to look at this and use it to explore a bunch of questions about quantum information, and you can see if you can make up your mind whether it's going to be science fiction, horror story, or whether there's some news. I often get asked, by the way, was Kennedy slain by hamsters? No, I think that's meant to be teamsters. Okay, so what is quantum computing and why is it of interest? And in particular, as the next generation of scientists, why should you have any interest in this at all? Well, first we need to step back and look at what information is. We're all aware of the idea of bits. So binary digits, classical information is encoded as zeros and ones. A 3-bit register can store any number, for example, between 0 and 7. In general, an n-bit register can store any one n-bit number. Quantum bits are a little bit different. They can be certainly a 0 or a 1, but you can have superposition of them. They can be 0 plus 1, 0 plus I1, or any superposition is possible. Consequently, they can store a lot more information. A 3 quantum bit register can store 8 numbers simultaneously. And in general, an n-bit register can store all possible 2 to the n numbers simultaneously. So there's an exponential blowout in the information storage capacity if you use quantum systems as opposed to classical systems. Of course, there's no good having that amount of information if you can't manipulate it or access it. So classically you use classical logic gates. For example, here's a NAND gate with the logic table underneath, and they're irreversible. There's 2 inputs that go in and 1 input that comes out. I'm not sure if many of you are aware, but of course there's a model of classical computation entirely based on reversible gates. A 3-bit gate called the Toffoli. Truth table shown there. It was shown in the 70s that any computer could be built solely from Toffoli gates. But there's an overhead to doing it, it's not economic, but you could build something like this just out of Toffoli gates. It was also realised in the 70s by Landauer that when you erase information with the irreversible gates, there's necessarily an energy cost. It's intrinsically inefficient. Whereas if you used only reversible gates, in principle you can have the most efficient computation possible. While thinking about that, people stumbled across the idea of what would happen if you used quantum gates. They must be reversible, and it turns out, yes, you can do logic with quantum systems, but you'll also end up with a strange possibility where the input is a superposition, say 0 plus 1. And then the output is an entangled state. And we'll talk a little bit more about entanglement in a few slides. Consequently, and this is, I guess, the take-home lesson for this slide, a 300 qubit register can store more information than the number of particles in the universe. Okay, that's a lot of information. And it's been proven in principle that there are problems that benefit. It's not that you can store the information and not do anything with it. And the problems that benefit a search, there's something called Grover's search algorithm. No, not the Muppet, a different Grover. Factoring. So this is the fact that a common encryption method is based on the fact that it's easy to multiply two prime numbers. You can do that. But if I give you a large composite number and say what are the prime factors, that's a hard problem, particularly as the number gets bigger and bigger. In fact, it's exponentially difficult with any known routine, but there is a known quantum computing routine that solves that. I'll come back to that. And then there's the problem of simulation, simulating other physical systems. And I think that's the most interest to this audience, and I'll talk about that later. So, if you're I'm told by my computer scientist friends that if you're a computer scientist, you have a very nice mental map of the world. All problems can be fall into one of two categories. Either they're insoluble, in which case they're not your problem, or they're soluble problems. And the soluble ones are the ones that computer scientists think hard about. And they subdivide into hard problems and easy problems. Easy problems are ones that can be efficiently solved, that is in polynomial time or not in exponential time. And by the way, I'm going to start, due to lack of sleep, using jargon and slang. If this happens and you don't know what I mean, please stick your hand up. Because if you're wondering, so will someone else will. Hard problems are things like the travelling salesman problem or the factoring problem. Now, watch very carefully because I'm going to show you what a quantum computer will do for humanity now. Watch very carefully. They'll make that easy problem area a little bit bigger. Quantum computers make some problems that used to be hard, easy. But they don't solve all problems. They don't even solve all hard problems, and they don't move us into the realm of insoluble problems. However, that little blue circle we're finding out contains a lot of problems, and it looks like it might contain all of quantum physics. So here's a recent quote from someone whose business it is to worry about encryption. In a world of quantum computers, we would need to abandon most of the algorithms that are in use today. There are other algorithms that could be used if there were functioning quantum computers, but they're uneconomic, really uneconomic. So no one's moving towards them at the moment. And I'm not going to work you through all this, but the last line, cryptographers are starting to take the threat seriously, and last fall many of them gathered at the PQ Crypto Conference to examine the alternatives. So this is from one of the trade magazines, IEEE Spectrum. And just the fact that quantum computers could exist have started sending the classical cryptography community, which is computer scientists, mathematicians, and people who worry about internet protocols, out to see if there are cheaper alternatives. Okay, let's look at factoring. I keep mentioning this. There's a thing called Shor's algorithm, which is probably the most famous of the quantum algorithms, and it takes a composite number into its constituent primes. And it's been described as finding a needle in a haystack. And here is the entire algorithm, so you can do it yourself at home. You take some number n which you've been given, you choose a co-prime. So that's something that has no common factor with n other than 1. And you solve that equation, CDR mod n equals 1. Now that's the bit that's exponentially difficult if you're using mathematical or MATLAB or any classical based computer. But if you have a quantum computer, that bit you can do efficiently. And then that gives you the number R, and you take that number R and substitute it in, and out pops the answers. So for example, if I give you the number 15 and ask you what the prime factors are, and you had brain damage and you're not able to do 3 and 5 in your head, you could do it this way. You could say, well, let's see, 4 doesn't have a common factor with 15, R ends up being 1, 4 to the 1 plus or minus 1 gives you the factors 3 and 5. That has actually been done in the lab in a variety of labs around the world, in Australia, China and the UK, and they did it for the problem of 15, which is obviously a toy problem. You can see there's still a needle in a haystack. It's just made the needle a lot easier and larger to find. It's not shocking that we know the prime factors of 15. Okay? But it was interesting because it's the very first time that we've done arithmetic that isn't based on the idea of counting on your fingers. All other arithmetic, because it's classical information, it's basically counting on your fingers very fast. Here, this is counting on entangled fingers. It's very early days. The algorithms that have been done in the lab are done on optical systems. They were done on something less than an optical bench in size. In fact, the most recent one that was published in Science last year was done on a chip the size of your pinky nail, but it contained a handful of gates, 2 or 3 gates. To do it properly, with no prior information, requires over 4,600 gates, just a factor 15. So where's the fuss? Well, the fuss comes about, yes, it requires 4,600 gates to factor 15, but then if I add, every time I add another qubit and a few more gates to the problem, I double the computational space. So I very quickly go from being able to factor 15 to being able to factor very large numbers. But that's not really why we get out of bed and think about quantum computing. The fact that Shor's factoring algorithm exists upset a lot of people. And I'm going to try and explain to you why it's upsetting. Although, as an experimental physicist, it's not upsetting at all. It means one of 3 things is true. There's something called the Church-Turing thesis about things that are computable, and there's a version of it called the extended Church-Turing thesis. And using it, you can show that you can't find an efficient factoring algorithm. So the fact that an efficient factoring algorithm exists means that the Church-Turing thesis is wrong, and that's the basis of modern computer science. Here's a quote from Michael Nielsen. The assertion of the Church-Turing thesis might be compared, for example, to Galilei and Newton's achievement of putting physics on a mathematical basis. What it did is it mathematically defined which functions are computable and opened them up into a way that you can scientifically talk about these problems. Or it's possible, the fact that Shor's factoring algorithm has been written down, it could be that the Church-Turing thesis is right and quantum mechanics is wrong. That would be really interesting. But as far as we know, the quantum mechanics tells us that we can do this. Scott Aronson at MIT, it's entirely conceivable that quantum computing will turn out to be impossible for a fundamental reason. This would be much more interesting than if it were possible, since it would overturn our most basic ideas about the physical world. The only real way to find out is to try and build a quantum computer. Such an effort seems to me at least as scientifically important as, say, the search for supersymmetry of the Higgs boson. I have no idea how far it will be in my lifetime. Oh, that's nice to hear. Well, the third thing is it's possible that, in fact, a fast classical factoring algorithm exists. That you could find a way of finding prime multiples. Apologies for the self-quote, but it's really hard to find an interesting quote by a mathematician. Basically, lots of mathematicians have looked and they don't think it can be done. So the fact that Shor's factoring algorithm exists means one of 3 things. It means at least one of them is true. And it means either computer scientists and or theoretical physicists and or mathematicians will be badly upset. Well, as an experimental physicist, that's a win-win. It's great. Doesn't matter what you do, it's interesting. And you piss off theorists, it's great. That's the negative reasons to do quantum computing. Well, in some sense. There's a more proactive reason, which is something called the Church-Turing-Deutsch principle. So this is the quantum extension of the Church-Turing thesis. And it hasn't been proven. It's a working principle, but it seems to be working very well. It's the thought that any physical process can be efficiently simulated on a quantum computer. We'll come back to that in terms of condensed matter chemistry in a couple of slides. Oh, actually. So, for example, most of modern physical chemistry, apart from the very hot and the very fast stuff, can be thought of about calculating where nuclei move on a potential energy surface. And here we show a typical one for a binding in, I think that's hydrogen. If you know the potential energy surface, you know nearly everything you need to know as a physical chemist. Equilibrium structures, transition states, reaction rates, nearly everything, as I said, apart from the very hot and the very fast. The trouble is calculating those surfaces, because they're using quantum mechanical systems, becomes exponentially difficult. As you add one more atom, you double the size of the problem. As you add one more atom again, you double the size of the problem. And so modern quantum chemistry, there's this tree of methods, computational methods, approximations, discrete this, blah, blah, that. I don't know them all. I have chemistry colleagues who do, and have painfully walked me through them. And the problem is, yes, some of the methods work in this area of chemistry, but they don't work here. And you worry that if I'm using this method, am I missing what's actually going on physically in the system? I need to go back and do experiments. It would be really nice to have a physical model that accurately described what was going on. So there's a possibility that you could replace all of that with quantum emulation. We'll talk a little bit about that later. And of course, so the first reason is why mathematicians and theorists, computer scientists care. The second reason is perhaps a reason why theoretical physicists should care. And the third reason is why most of the people in the labs care, which is quantum computers are interesting physical systems in their own right. So shown here, this is just a bunch of images of recent systems where they've been able to show quantum coherence, entanglement, and manipulate systems at the quantum level, preserving their quantum properties. And that's a really fun thing to be able to do. From left to right, we have ion trap, photons in a circuit, neutral atoms in the lattice, and on the rightmost image is a superconducting circuit. And on the whole, there's about 6 systems now where people can reliably walk into the lab and get quantum behavior. Which brings me to the issue of physical implementations. If we think about where we are with quantum technologies, theory is about here, and experiments a little bit behind. I like to use a quote from Popular Mechanics in March 1949, where the ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons. Computers in the future may have only 1,000 vacuum tubes and weigh 1.5 tons. Well, they were right. Okay, the computers did get smaller. I don't think anybody saw in 1949 this kind of thing, right? So keep in mind that when we're talking about the future, I'm going to be probably right on the timescale of the next few years and massively under-ambitious on the timescale of 20 years or more. So if you're going to build a system where you're trying to retain quantum properties, or properties of quantum information, you're going to encode information into the quantum system, and you want it to be there later when you come to look at it. David DiVincenzo in the 90s came up with, well, eventually there were 10 or 12 commandments, but the first 5 are what concern us here. First, you need to obtain well-defined qubits. That is, you need a 2-level quantum system that you can nicely control. Secondly, you need to be able to reliably prepare initial states. There are quantum systems where you can easily see 2-level behavior, but it's hard to, say, make everything in the ground state. The third thing is you need to have the qubits well isolated from the rest of the universe until you want them to interact. If they interact constantly, they're bleeding information out, and it's called decoherence. You need to be able to bring the qubits together and entangle them, and we talked about that earlier with the entangling gate. And then finally, you need to be able to measure the outputs of the system and see what's going on. I'm going to just skip, okay, no, this is fine. So, has this been done? Well, yes. It turns out that in the past 15 years, people have looked about just about any kind of physical system to try and encode quantum information. I think my favourite, halfway down the list on the left, is electrons in a helium film. Right? This sounds completely whack, but it's actually quite a nice idea. So I'll take electrical circuit with some electrical structures underneath, put the whole thing in the fridge, put a thin film of helium, and then inject single electrons which float on the helium, and then you can pin them in place using the electrical circuits, control their interaction using electrical circuits. Okay, it sounds weird, but it's no weirder than anything else that people have tried. And the degrees of freedom of these quantum particles that people have used, pretty much anything that you can quantize. Spin, energy, momentum, direction, flux. I guess when a lot of us did our undergraduate quantum courses, we got introduced to the idea of quantum mechanics through the idea of spin and the Bloch sphere. Just as a matter of interest, how many people, this was their first place they saw quantum behaviours? Yes, no, hand up. No one has ever done quantum mechanics in their life. God, you're always the first years. Guys, get some coffee. It turns out the quantum information is powerful because suddenly communities that would not speak to one another, even 10 years ago, for example, condensed matter physicists don't like talking to laser physicists and vice versa. But we've suddenly got a common language, which is the same way we look at these systems and quantize them. We can also talk about atomic, molecular and optical systems. Here we are with ions, for example, in a trap, or polarization of light. And it turns out we have a common language between what had been up until now a bunch of different physical systems. So this is adapted from a very old now US roadmap on where progress was going with quantum systems that people are looking at. NMR, trapped ions, neutral atoms, a whole bunch of things. The green dots is good, red is bad, and basically there's no red left. Nothing yet is all green. There is no system where people are going to be able to build you tomorrow a nice big quantum computer. But progress is happening pretty steadily. Are there any questions on any of this? This is kind of background. No? Okay. Right. So that brings me to photonic quantum computing. So this was one of the early systems where people looked at quantum behaviour and in the real sense because it was easy to do. If you're going to store information in light, you need the particles of light, which are photons. The way that they're most often produced is you take in purple, you see a high energy laser beam, you pass it through a nonlinear crystal, and spontaneously, about 1 time in a million or so, a pair of lower energy photons is conserved. And if you take into account the crystal, it conserves energy and momentum. If you look at a photon in one arm, so they're called, due to 1940s radio technology, the signal and idler photons. But just think of them as the top photon. You look at the top photon, because the two photons are created from the same mother particle, they're born within a few femtoseconds of one another. So if you find a photon in the top path, then with very high accuracy, you know there's one photon in the bottom path. And in fact, it's something like 99.999% of the time there'll be a photon there. There's a small possibility that there'll be two photons there, because what can happen is instead of this photon giving you two daughter photons, you can have, within the same very short time window, two photons both split. And then if you don't have perfect detectors here, you might count one photon here, but there'll be two photons in the other path. It turns out that doesn't happen a lot of the time, but it becomes a problem when it does. People very well know how to manipulate these systems to get the light out and get them into, these days, integrated waveguides and optical fibers. This is just a movie of what happens as you're looking at the down-converted photons and tune the crystal. It's a bit like the Chanel symbol, I quite like it. And in a period of about 12 years, they've come up 7 orders of magnitude of brightness. So these things are now bright enough that you can just walk in the lab and see the down-converted photons with your eye. And in fact, they're so bright that our biggest problem now is if we send that many photons into our detectors, they blow up. So sources are not a problem from the point of view of brightness. I said earlier, you can use any degree of freedom that you can quantize. So for photons, there's not many degrees of freedom. You can use the polarization, encode information in that, horizontal, vertical. You can use the spatial pattern. When I point this laser on the wall, I'm seeing basically a round dot. But I can make lasers where I have dark lines and spots in the middle, and I can encode information in that as well. Just sending photons in different paths can be an encoding. Having them arrive at different times can be an encoding. And having them at different energies can be an encoding. And all around the world, in about 20, 25 different groups, people have used mixtures of these encodings. It doesn't matter what you use, you have to be able to make a coherent superposition of your two-level quantum system. So if, for example, you're going to use horizontal and vertical polarization, coherent superposition of those might be light circular. That's very easy. Spin up, spin down, something on the equator is a coherent superposition. The other two things you need for a quantum computer is, okay, you've encoded information as two-level quantum systems. We'll come back to what happens later on Friday if you encode it into multiple-level quantum systems. You've encoded it into a two-level system. The first thing you need to be able to do is move it around the Bloch sphere, or the Poincare sphere, or whatever you're used to calling it in your field. In polarization, that's very easy. You can use wave plates and get anywhere on that sphere. What's hard is having the photons talk to one another. If I take this laser pointer and I take another laser pointer and I shine them through each other, the beams of light don't bounce off one another. Actually, it turns out if you did it with a LIGO-sized field, so something with very, very high intensities in a vacuum, there's a very small scattering cross-section, but it's tiny. So for all practical purposes, photons don't interact with one another and we want them to. So how do you get photons to interact with one another? The most obvious way is you send both of them into a material and you get a nonlinear optical interaction, and that's done all the time. In fact, if I had a green laser pointer, which I don't, the green light is coming about from frequency doubling, which is a nonlinear interaction. The problem is if you go through the numbers, that gets more efficient the more photons there are. And if you look at the numbers when there's one photon each, and I want them to double up, it doesn't happen. In fact, getting two photons to interact with one another is just impossible. So Gerard Milburn, who's a professor here, back in 1988 published a paper that said, if you could do this, you could do quantum computing. Wouldn't that be a good thing? And the paper was a little bit ahead of its time. It went off to the Australian Research Council as a fellowship application in '89, and they got a referee's report back that said, if you fund only one project in Australia this year, make sure it's not this one. Okay? It was just seen as, come on, it's impossible, it's science fiction, you're years ahead of the time. So there is a solution. Let me just take a break for a second and point you to a lovely book by Leon Lederman called The God Particle. And it's about the search for the Higgs boson. In fact, the worst thing about the book is its title. The best thing about the book is at the beginning he's got a glossary. So if you've got parents who ask you, what is it that you do all day? This is a nice book to give them. And there's a glossary for your parents, and it defines an experimentalist as a physicist that does experiments, and a theorist as a physicist that does not do experiments. So for the next few slides, I'm going to be a theorist. I'm going to talk about proposals and things that haven't been done. Okay, so how do you get two photons to interact? Well, the first proposal, this is a table, was Gerard Milburn's, the idea that you just find a strong nonlinearity that doesn't exist. So that didn't have a lot of legs. The next thing was something called linear-optical, and we'll come back to that in a little while. Then something called interaction-free measurement, quantum Zeno effect, amplified with nonlinearities, and then most recently, geometric phasing in space. It's jargon. The important thing is whether the text is white or black. The black text is a proposal where they bring in the idea that measurement is powerful, that measurement is a nonlinear process, that having measured a quantum system, you've got an irreversible change, and that looks like a nonlinear effect. And there is something called the measurement problem in quantum mechanics. Where do you draw the boundary between classical and quantum? As an experimentalist, I think the measurement problem refers to the people who worry about it as opposed to the physics. But here, this is an application of the idea that measurement is powerful. So we'll play with that a little bit now. First, we'll look at the quantum Zeno effect. In 2004, a physicist in Maryland in the US said, well, look, you can get a nonlinear interaction using loss. Actually, I'm slightly out of order here. Let me skip ahead. I'll go back to the granddaddy idea, the one that started it all. So let's look at this linear optical. So Gerard Milburn, again, having disgraced himself in '88 by coming up with an idea that would never ever work, remedied himself in 2001 with some colleagues at Los Alamos, where they said, here's how you can get two photons to interact. You can take single photons, send them through a linear optical network. This is just mirrors, phase shifters, lenses, nothing nonlinear. And they will come out entangled, looking like they've interacted with one another, if you allow yourself some additional single photons, single photon detection, and feed forward. So it's the idea of measurement and then conditioning of things on measurement makes things look like there's been a nonlinearity. That was a very powerful idea. It's a little bit weird too. It's built into quantum mechanics that this should work. There's no reason that this couldn't have been discovered in the 1960s or 70s, but it's just that people's heads, I don't think, were in the right space. It's a very subtle idea. Lots of experiments have been done based on it. Part of the subtlety is when you do this and the photons come out, some of the time when you send the photons in here, you don't get signals here. And so the things that come out, it hasn't worked. Or some of the time, photons that come in here end up getting absorbed by these detectors. So the gate doesn't work 100% of the time. And that looks useless, right? Because if I've got a gate that only works a quarter of the time, and now I need to have two gates to do a calculation, it'll only work 1/16 of the time, and I'll get this exponential cost in trying to do anything. But the secret is, you get a success signal. When all the detectors go off, you know the gate works. The rest of the time, you can ignore the inputs. So then if you combine that with teleportation, no, terrible thing. Teleportation is moving information around without measuring. Okay? So the idea behind teleportation is, say, the following. Say I had some quantum system. Let's see. I'm going to try and move its information across the page here. Well, if I send it in, this is a pair of entangled particles. I take one of the entangled particles and I do a joint measurement with this quantum particle. I get two classical pieces of information, 0, 1 or 0, 1. I feed those forward and I recreate the state of this particle. The state of the particle, not the particle. Even though I don't know what the state of the particle was. To define a quantum state, 0 plus B1, that requires an infinite amount of information. I've got two pieces of information out, 2 bits literally. And that, along with the entanglement, contains an infinite amount of information. It doesn't tell me what the state is. Measuring those bits don't tell me what's going on. So that's how a teleporter works. Now that looks like an awful lot of trouble if you want to send information across the room, particularly if you want to send information across the room with light, you can just send it across the room. Right? It doesn't look like you gain. But you gain in a situation where if you then take 2 teleporters, which looks like twice the hassle, and then take one of these non-deterministic gates, what you can do is you can start running these entangled states through the non-deterministic gate. And you keep asking the question, did it work? Did it work? Did it work? Meanwhile, you bring in the qubits control and target here that you're wanting to send into your logical gate, and you put them in your perfect quantum memory. You've gone down and brought it came up. You run this until it works, and eventually it will work and give you a success signal. When you pull these things out, you send it through these measurements, you do some feed forward, and it now looks like you've done an entanglement gate. That's an awful lot of work. But it does, in principle, teleportation makes non-deterministic gates deterministic. A lot of gates have been proposed. They fall into 2 categories. There's ones where the photons are intrinsic to the operation of the gate, so you need those to see the logic. And there's ones where you can just look at the gate, it won't scale, but you could later on bring in extra photons to make it scale. I.e., this gate itself doesn't work all the time, but if you added some extra photons afterwards, you could make it work all the time. In principle, if you take any of these proposals and you add teleportation and you add error correction, you add a scalable quantum computer. That slide is describing 25 years of development to come, so it won't happen soon. I lied to you, quite shamelessly, just then. I feel good about it. I said that if I take in this entangled particle and this quantum particle here, and I do this joint measurement called a Bell measurement, John Bell, an Irishman who worked at CERN, it'll work. I'll make the thing work all the time. Except I lied to you because I know Bell measurements only work half the time. Okay? So that means this gate only works a quarter of the time. So this intrinsic gate here works, say, 1/16 of the time. Now I've made it work 1/4 of the time. It's still not 100%. I'm not winning. my teleporter is broken. And if we turn to the source of all wisdom on teleporters, The Simpsons, we know broken teleporters are bad news. So how do we fix it? Well, in their paper in 2001, Parnell, Laflamme and Milburn realised that they had to fix it. And the way they did it was the kind of solution only a theorist could love. It's in two parts. One, you need to increase the number of entanglement that you've got as a resource, and two, you need to increase the number of gates. And just to give you a sketch of it, this circuit looks more complicated than the circuit I had on the previous slide because there's a more complicated entangled state going in. And then I need a lot of them. So if I wanted to bring 2 qubits into a gate and have it work 95% of the time, this is so level 1 encoding, there's a big entangled state there, it works 4/9 of the time. You go to a level 2 encoding, which is a bigger entangled state, it works 9/16 of the time. Well, if I had those big gates, I would need 300 of them to get a single logical gate that works 95% of the time. It's still not 100%, and it's tens of thousands of optical elements. It would be a fairly large experiment. And in fact, to get it to work perfectly, I need an infinite number of gates. So clearly this is not really a way forward. I gave this slide a few years ago at a winter school in Taiwan. And the only question I got afterwards was, excuse me, Professor White, is that one of your students? To which I answered, no, but I'm quite sure they would all scream like that if I got in the shower with them. Okay, so that's horrifying, right? Not the shower, the actual physics. Is horrifying. This is not the way forward. So it turns out you need to change how you think about quantum information. So in a conventional logic circuit, you have information flowing through the circuit. It goes from left to right, you go through single gates, these red lines are 2-qubit entangling gates, and at the end you read the information out. But in quantum mechanics, you can do things differently. You can have a flow of measurements. We've just said measurement is powerful. So what you can do instead is these circles now represent qubits, the red lines represent entanglement, and you make some large, you take your qubits and you entangle them together in some special way, and then you do a flow of measurements across the circuit. So first you do some measurements here, alpha, beta 1, and then depending on the results of that measurement, you do measurements plus or minus alpha 2, beta 2 there, and so on. And you flow the measurements across. So if you could make a large entangled system, you could just do a wave of measurements and the outputs contain the answer that you're after. And this is because, as we've already said, measurement is powerful in quantum mechanics and entanglement isn't powerful. That's fine. How do you do that entangled state in optics? Well, you could use these non-deterministic gates. So I said a level 2 gate works more than half the time. You could just keep flipping the coin. Did it work? Yes, great, they're entangled. Did it work? Oh no, I got rid of them. Did it work? Yes. And you could just build it up. Now, photons are notoriously hard to hold. They move roughly at the speed of light. So they're not good for hanging around. They're not what we call a stationary qubit. But this cluster state idea that you entangle, you can build as they go. So I'm going to give you a visual metaphor now so that you will hopefully remember that point. There we go. So what you could do is build your entangled state as you go, doing measurements on the fly, throwing photons away as you need, and you're doing a measurement with the line as fast as you're building the entangled state. Now, clearly it's a bit hectic. There might be better options, but it works if you're stuck. Okay, so that's called a cluster state or a graph state. Now, why are people interested in that? Well, A, it doesn't require many tens of thousands of resources per gate. The green points here show the number of physical resources required for a single gate that works well. And it's dropped from tens of thousands to hundreds. Hundreds is still not good, but it's better. And the pink points show how much data, how much loss you can cope with. I said a gate works 95% of the time is better. Why did I say it's better? Well, we come back to a subtle idea, and I'll talk more about this on Friday, about loss tolerance. So it turns out your classical computers, the gates are built, we know that they fail. And in fact, when you buy a chip, if you're amping up your game machine at home and overclocking the chip. What you're doing here is the chip is built, it's got a certain level of failure, and they know it works reliably at a certain clock rate. And that's how they sell it to you. And there's a certain amount of error encoding. Error encoding is hard in quantum systems. So what you can do is you can find ways that you can cope with the fact that if you measure a quantum system, you destroy the information. So if I've got a quantum system here, and it accidentally gets measured, that's it, it's lost. So what I can do is take that quantum system, entangle it to something else. If this gets accidentally measured, there's a protocol that I can use to retrieve some of the information. This is called, fault tolerance, error encoding. And it turns out that originally it was thought gates would have to work 99.9999% of the time. You could have one part in a million errors. It's now believed you can have errors up to a third and still cope. There's a trade-off between the pink and the green curve. The less errors you have, the less resources you need. So if you've got a bad system, you'll need a lot of resources to encode. That's an ongoing thing, and this is an old slide. Okay, so that was me being a theorist. Let's talk a little bit about practice. There's a computer scientist, now deceased, from Caltech, apparently very famous, called Jan van der Stepschoot, and if there's any Dutch people, I apologise for my horrible accent. In theory, and he was talking about classical computer science, in fact classical computer programming. And he said in theory there's no difference between theory and practice, but in practice there is. How am I going for time? Need a break? Okay, let's stop there. It's a good point to stop. We'll come back and do the next 45 minutes later.
Questions for this first lecture? Sure.
Or we can do it. Oh, there's a question? Yes.
Sorry, Kishan.
Sorry. I was just saying the active feed forward. Is that not a limiting step though for the system? It's slow. Because how fast can you make that to actually?
Okay, so the question is the active feed forward a limiting step to the system because it's slow? In fact, it's the limiting step in these optical systems. So at the moment, the fastest gates have been shown to work in optical systems with the feed forward at about 150 nanoseconds as the feed forward step. Unpublished, but colleagues in Vienna have got that down by an order of magnitude, down to about 15 nanoseconds. Eventually the limitation will not be the electrical feed forward, it'll be how long it takes to turn a photon into an electrical current to be detected. So it's that combination of detecting the photon and then moving forward and then moving an actuator. Now in these cases the polarization is being changed, so you can do that with electro-optic circuit. So if you're in a waveguide, that can be very fast. Commercial waveguide modulators working gigahertz up towards terahertz. So we're thinking we can get it down to a clock rate of tens of nanoseconds or nanoseconds, but you're absolutely right, it's the limiting step for this particular approach. For any quantum system, if someone comes to you and goes, psst, you want to buy a quantum computer or a qubit, the thing you need to ask them is what is the ratio of gate time to decoherence? So the decoherence on photons is very good. If you look at the cosmic microwave background, it's polarized, partially polarized. So you know photons can retain partial coherence for 15 billion years. That's quite good. They don't interact with anything. Okay, solid state systems are slightly worse. Anyway, let's have a break.